Okay, let's pick up again. So we talked about how sinusoidal waveforms can be mathematically represented with the equation V of t is Vm cos omega t plus or minus theta. So if you look at, is it not? If you look at this waveform, let's go back here, any waveform basically, any sinusoidal waveform, we note that it is exactly symmetrical around the x-axis, right? So you have a positive value and you have a negative value, and both are exactly the same. So what is the average value of this waveform? Zero. Only one student knows. Zero, right? This is exactly symmetrical around the x-axis. So the average value, mathematically, if we try to describe the average value, it would be zero. But energy is still transferred. If you have a AC source connected to a circuit, it will transfer, will send energy to the components, right? So how can we mathematically describe an average value for this waveform? Well, faced with this conundrum early on, what they decided to do was, instead of taking the average, mathematical average of the waveform, what we will do is we will square the waveform first, and then we will take the average. Okay, so you square the waveform first, then you take the average. So now you have a non-zero number, but because you took a square at the beginning, now you have to take the square root at the end of that average. And so they came up with a new term called root mean square. It literally is the square root of the mean of the square of the waveform. Okay, so you have the waveform that you describe mathematically, V of t or I of t for that matter. You take the square of the waveform. And once you take the square, you want to take the mean. Mean, of course, is nothing but summing up everything and then dividing it by the time period. So you have one time period. You have one time period. You take individual slices, which is dt, right? dt. And then you sum up the sizes from 0 to t, which is the integral 0 to t for that one time period. And then you divide it by t because you're trying to find the average. And because we took the square at the beginning, we'll take the square root of that result. And hence, we obtain a value that is known as the root mean square, or more commonly known as RMS. RMS. Okay, so RMS value of the waveform is what the average value of the AC waveform would be. It is the equivalent, it is the AC equivalent value that would describe the same energy as a DC value. Okay, so if you have a resistor, if you have a 1 ohm or 10 ohm resistor, if you apply a DC value to that resistor, you would expect to have some power associated with that resistor. An AC RMS value would have the exact same power or energy in that same resistor. Okay, but it is not a it is not the average value, because the actual average value would be 0. So RMS is not actual 0. Does that make sense to everyone? Okay, that's what the RMS value is. Okay. When you plug in V of t or I of t as Vm cos omega t in that equation and we solve it, there is a derivation, of course. And when we do that, derivation, it turns out that the relationship between RMS and the peak values is given by this equation. Vm or V peak is √2 times the RMS value for sinusoidal waveforms only for sine and cosine waveforms. Okay, only for sine and cosine waveforms. This does not hold true for any other waveform. Only holds true for sine or cosine. Okay, only for sine and cosine. So it's a quick and easy way for us to determine what the RMS value is. Now, at this point, I'd like to ask, take a guess at what quantity is being represented by the 120 volts of our power outlet. Is it RMS or peak? Wild guess. And explain the logic later. How many of you say RMS? How many of you say peak? Okay, 1 peak, 2 peak, 3 peak, or no peak? No peak, no guesses. Okay, so peak is a good guess, but here's the logic though. If it describes only one value without stating it's a function of time, then it's almost certainly a RMS value. Because RMS is basically something like this. So let's say you have a waveform that looks like this. Now, think of them as mountains of dirt. Okay. You transformed all negative peaks into positive peaks, and then you flatten out these mountains into a plateau. Okay. When you flatten out all these mountains of dirt into a flat plateau, that is the RMS value. And this is the peak value. Make sense? So RMS value will always be lower than the peak value, and it's a single fixed value. RMS would be a single fixed value. So unless a statement or a value is given as 10 volts peak or 10 volts peak to peak, it is always safe to assume that that quantity is RMS. So if we say 120 volts from the power outlet, it's RMS value. Make sense? All right, let me know if you have any questions. Yes. Root means square. So square root of the mean of the square of the waveform. All right, any other questions? Okay. So then we get into the math. Okay. Now, we won't talk about like Fourier analysis and differential equations. That's not my idea of a good time. Okay. The biggest advantage we have is when we have a sinusoidal and we apply it to a circuit, the resulting voltages and currents are also sinusoidal in nature. The shape of the waveform doesn't change. Okay, the frequency of the waveform also doesn't change. What does change is the magnitude or the amplitude. The y-axis value changes. If we think about DC circuits, let's say, for example, you apply 10 volts to a circuit, and the resulting voltage at some point in the circuit might be 5 volts, right? So what has changed? The value of that voltage has changed depending on the value of the resistors, the capacitors, or the inductors in the circuit, right? For AC, this is for DC. For AC, what happens is if you apply 10 volts, you might get 5 volts at a certain point in the circuit, depending on the component and the circuit configuration. Plus, the phase also changes. The frequency does not change. Okay, the frequency does not change. So mathematical calculations in AC circuits involves us trying to find not only the amplitude or the magnitude, but also the phase. In DC analysis, we only need to find the magnitude or the value of that waveform. In AC, we have to find and calculate the phase also. But the good news is that the result is also a sinusoidal, right? Because if you take, let's say for capacitors and inductors, you apply a sine or cosine waveform. Capacitor and inductor, we have to find derivatives and integrals for voltage and current. L di over dt, C dV over dt. If you apply a current to an inductor, if you apply a voltage to an inductor, VL is di over dt, derivative of the current. If the current is sine x, what is the derivative of sine x? Cosine. What is the derivative of cosine? Sine, right? So sine and cosine, the derivative and integral of a sinusoidal waveform is also a sinusoidal. And so it makes it easier for us. When we generate electricity, a generator has a magnetic north and south pole. It rotates inside a circular motion, right? Whether it's wind power or it's hydroelectric power, it is a turbine that is rotating in a circular motion. And so that circular motion generates electricity that rotates between a north pole, south pole, north pole, south pole, and hence we have a alternating sinusoidal waveform. And we don't change that waveform, use it as it is. So mathematically, what we are going to do is we are going to use complex number math. Complex math or complex number math. And we're going to use the imaginary number. How many of you have used the imaginary number complex math in your own engineering fields? Some of you may have, some of you may have not. It is not specific to electrical engineering, obviously. Imaginary number is a mathematical concept. It is not imaginary in real life. Okay, it is not imaginary. There is a physical basis. We don't have time to get into all of that mathematical concepts, but imaginary number does not mean it is imaginary, just as fractions are not imaginary. Okay, if you start counting real numbers, and we say real numbers are 1, 2, 3, 4, 5, 6, and fractions are not real numbers, but fractions are real. Does that make sense? They have a physical basis in real life. Decimal has a physical basis in real life. So same way, imaginary numbers in mathematical terms, we state it as imaginary, but it has a real basis. So imaginary number I is what we're going to use. But what is I in electrical engineering? Current. So in EE, we will replace the I with J. Okay, we'll replace the I with lowercase j. And I'm fond of this phrase. We use complex math to make the math less complex. Okay. And what we're going to do is we are going to represent sources and our components both with complex numbers. Okay. In order to make our math less complex. Without using the complex numbers or complex math, we would have to solve differential equations. Okay, differential equations. And again, solving differential equations is not my idea of a good time. I don't know about you. Some people like to do that, but not me. Well, thankfully, greater minds have come before us and they have outlined the math that we need to use. And what this does is it reduces differential equations to simple circuit analysis problems. And when I say simple circuit analysis problems, I mean we do not have to do L di over dt or C dv over dt. We can simply apply V equals IR, Ohm's law. All the circuit analysis techniques that we learned earlier in chapters 1 and 2, we can apply exactly the same techniques, except now we use complex number math. Okay, let's take a pause, think over that. Let me know if you have any questions. Any questions? Okay, so what we're going to do is we're going to learn a bit about phasor transform. Okay, so sources are converted to a complex quantity known as phasors. Okay, these phasors are not the ones from Star Trek. They're not going to stun you or kill you, but they will scramble your brains on occasion. And then we have our components, resistors, capacitors, and inductors. Thankfully, resistors are not energy storage devices. So they behave exactly the same way for AC as they do for DC. Okay, so resistors will not affect the phase of the voltage or current. They will only affect the magnitude. If you apply a 10 volt AC voltage to a 10 ohm resistor, the resulting current will be 1 amp. Okay, the phase is not affected. But inductors and capacitors are energy storage devices. There is a phase difference between the voltage and current for a capacitor and an inductor, because the energy transfer does not take place in an instant. And so what we're going to do is we're going to represent capacitors and inductors as complex quantities known as impedances. Impedances. Okay, impedances. And the word impedance comes from impede. And we'll learn about complex impedances in just the next few slides. Okay, let's take a look at our sinusoidal waveforms first. How are we going to represent the sinusoidal waveform and the complex impedances? Well, as I stated, we represent them using complex numbers. We're going to use vectors to represent both complex impedance as well as the source in terms of a phasor. What do we need to describe a vector? Absolutely, magnitude and direction. The magnitude is basically the length of the vector. The direction is given by the phase angle. And the phase angle comes from the phase of the waveform, which was in degrees. And this is the reason why we keep that phase angle. We keep the phase as a separate quantity in degrees. It's because we need that information to describe the vector for the source. Okay. So here is a image of a sinusoidal waveform in the time domain. It's rotated by 90 degrees. Here is the y-axis in time. Sorry, not y-axis, the x-axis in time. So this is in seconds. That's time t. And this is the y-axis, the voltage in volts. And as you can see, this is not to scale. Okay, it's not to scale. This is this far away. From time t equals 0, right? This is time t equals 0. So V of t is Vm cos omega t plus or minus theta. Theta, of course, indicates the phase. Phase indicates the moment in time when it crosses the x-axis, point in time where it's going to cross t equal to 0, or how far away it is from t equal to 0. When you transform it into the frequency domain, which is basically the complex plane, the complex plane has the real axis and the imaginary axis. What we are doing is we are taking the sinusoidal waveform and we are describing it as a circle. Circle can be described in radians as 2 pi radians or 360 degrees. Okay, 2 pi radians or 360 degrees. So one time period, one full time period is 2 pi radians or 360 degrees. Half, this is also known as a half cycle. So a half cycle is pi radians or 180 degrees. And a quarter cycle is pi by 4 or 90 degrees. Let's take a pause. Let me know if you have any questions. Any questions so far? Okay. So vector needs only two things to describe it, magnitude and direction. In our case, it is the length that comes from the value, the peak value of the waveform. And then the phase angle comes from the phase of the waveform. And we can write the phasor, for the source directly from the time domain expression. Vm with an angle of theta. Okay. So a sinusoidal waveform can be represented as a rotating vector in the complex plane. The vector is rotating in a counterclockwise direction. This is very important. And this is very important. It rotates in the counterclockwise direction. Starting point is 0 degrees or 360 degrees. Top end here is 90 degrees. This is 180. This is 270 degrees, and then of course 360. And you start off in a counterclockwise direction. So positive angles, positive phase angles means the vector is rotating in a counterclockwise direction. Negative phase angles mean that they're rotating in a clockwise direction. Okay. Positive angles mean they are rotating in a counterclockwise direction. Negative phase angles. So if a waveform had V of t is 10 cos of omega t minus 15 degrees, then it is rotating in the clockwise direction. One thing to note, the phasor is a single snapshot at one single point in time. Okay. It is a single snapshot of the waveform. It does not contain any frequency information. We say it is rotating. It's a rotating vector. Okay, but it's a single fixed snapshot. Hence, it does not contain any frequency information. Even though we say it is rotating with a speed of omega. Okay, it does not contain any omega information. It's simply the magnitude and the phase angle. That is it. Only two things, magnitude and the phase angle. Vm with the angle of theta. Does that make sense to everyone? The transform process of going from the time domain expression to the complex number is known as the phasor transform. There is a derivation, of course, that we show for EE classes, but not for non-EE major classes. If any student is interested, I'd be happy to discuss it during office hours. Are we all good on the phasor transform? Any questions? There's a lot of technical information to take in. So even though you may be familiar with some of the concepts, when you're trying to solve circuits using this, you need to move at a faster pace. So there's a ton of information that you would need to review. Again, let me know if you have any questions. Okay. Then let's go to impedance. Impedance comes from the word impede, same way as resistance comes from the word resist. Resist, of course, means we're resisting or opposing the flow of electrons, the flow of current. Okay. So all three words are kind of synonyms in this case. We have impedance, resistance, and reactance. Okay. So these are new terms. Let's see what each one of those means. Resistance is a property of resistors. It's direct opposition to the flow of current. Okay, it's direct opposition to the flow of current. Ideal inductors and ideal capacitors do not have any resistance. They are energy storage devices. They do not directly oppose the voltage or the current that is applied to them. Hence, they have 0 ohms resistance. Does that make sense to everyone? Ideal capacitors and ideal inductors do not resist the flow of electrons. They do not oppose any transfer of energy. Hence, ideal inductors and ideal capacitors have 0 ohm resistance. Okay. Now, when you have energy that is stored, let's take the inductor for instance. The stored energy in an inductor will give rise to a magnetic field, and magnetic field gives rise to a voltage that has opposite polarity to the input current. Okay, so let me explain this diagram. Let's say current enters the inductor from the left. So the voltage would have plus on the left, minus on the right. After some point, the inductor will reach full charge. Once it reaches full charge, this inductor voltage would go to 0 volts. So plus minus would not matter. Now, if you try to change the value of this incoming current, the stored magnetic field, stored energy in the magnetic field will oppose any change in the value, of the input. And that opposition is a reaction to the change. Hence, that opposition is termed as reactance. It is not direct opposition to the input voltage or direct opposition to the input current. Hence, there is no resistance. But there is a reactance. There is a reactance which opposes any change in the input. Critical difference. It is not opposing the input itself. It is opposing any change in the value of the input. And that is termed as reactance. And collectively, we describe the resistance and reactance together as impedance. It impedes. The impedance can be describing direct opposition in case of resistors, or it could be describing just reactance in case of inductors and capacitors. But collectively together, we came up with a new term known as impedance. So when we deal with AC circuits, we typically talk about impedance. For a resistor, X is equal to 0. Hence, impedance of a resistor is simply the resistor itself. There is no difference. There is no such thing as an impedance of a resistor. We simply say it's a resistance. That's it. Because a resistor behaves for AC exactly the same way that it behaves for DC. Okay. So resistor X is 0. Reactance is noted by uppercase X. Resistance is noted by uppercase R. Impedance by uppercase Z. Z is represented as a complex quantity. Remember, I said we describe it all together collectively. So it describes as a complex quantity R plus JX. R plus JX. J is the imaginary number I in electrical engineering. So R is stated as real portion of the impedance, which is resistance, and X is termed as the imaginary portion of the impedance. But there is nothing imaginary about reactance. It has a physical basis in real life. It is only the mathematical, it is the mathematical representation that we term as imaginary. Okay, oftentimes you might read imaginary reactance, okay, or imaginary impedance, imaginary reactance, but that imaginary is only referring to the mathematical representation of reactance. It is not representing, the reactance has a physical basis in real life. It is real. It is not imaginary, okay? So if you hear the term imaginary reactance, it's talking about the mathematical representation only. Let's take a pause. Let me know if you have any questions. Any questions? Okay. So for an inductor and capacitor, the resistance is equal to 0. So all they are left with, the impedance of an inductor and capacitor is XL and XC. Okay. So for a resistor, the reactance X is equal to 0. So ZR, impedance of a resistor, is equal to R. For an inductor and capacitor is the exact opposite. The real portion resistor is equal to 0, but the reactance is non-zero. So ZLZC is XL and XC. And because we are using the imaginary number to describe it, we also put a J in front. So it's J times XL and J times XC. Actually, for XC is 1 over J. 1 over J. And because we are using both polar coordinates and rectangular coordinates to describe it, we can describe what is known as a graphical illustration for the impedance as the impedance diagram. Impedance diagram. Okay. The impedance diagram is plotted with the resistance R on the real axis, the imaginary reactance on the y-axis. And when you join the two vectors together, you get the magnitude of the impedance along with the phase angle. And so the impedance diagram notes our quantity. R plus Jx is equal to magnitude of Z with a phase angle of theta. Magnitude of Z with the phase angle of theta. Does that make sense? Any questions? Fundamental laws all remain the same. I'll come back to this slide after I talk about this. Ohm's law, V equals IR, in AC now becomes V equals IZ. So think back to chapter 3, where we had to find the inductor voltage, and we would need to perform a derivation or an integration if it was a capacitor. So L di over dt and VC, capacitor voltage, would be C dV over dt. And then we'd have to find the integral if you wish to find the other quantities. So IC is C dV over dt. Instead of doing this, all we'd have to do is find the impedance IL times ZL. VC would be IC times ZC. No need to perform derivation, no need to perform integration. We simply apply Ohm's law as it is. Okay, so VR is equal to IR times R, IL times ZL, IC times ZC. KVL, KCL, all our equations work exactly the same as they did for DC, except each one of these quantities is now a vector. Each one of these quantities is now a complex number. It has a magnitude and it has phase. Okay, so all the fundamental laws work exactly the same. Impedance. Okay. It'll work exactly the same. Impedance is represented by the same notation. So impedance, resistance, or reactance are all noted by the same symbol, the zigzag symbol, and the units are ohms for all three. So when you have two capacitors in parallel or series, if you have something like this and you convert it to its AC circuit, you can represent each component with its impedance. So this would be ZC, this would be R, this would be ZL. And depending on the circuit configuration, if you have the impedances in series or parallel, they combine the same way as resistors. except it is a complex quantity. Okay. So impedances in series and parallel are combined exactly the same way as resistances. Note again that a capacitor cannot be combined with a resistor. It cannot be combined with an inductor. But if you have an AC circuit, you convert it into an impedance and you can combine the impedances together. So you can combine an impedance of a capacitor along with the impedance of a inductor, and you can reduce them, whether they are in series or whether they are in parallel. It's a big difference. Okay. So now let's go back to this slide and we'll talk a little bit about the math. Okay. We took a time domain expression for our source. We represented using complex numbers as a vector. That vector is known as a phasor. It has a magnitude and it has a phase angle. Magnitude, let's say, is noted by r, or the length of the vector, and theta is the phase angle that it makes with the real axis. Okay. If you project this vector on the real axis and the imaginary axis, the projection, the length of the projection of these vectors on the imaginary and the real axis gives you the rectangular coordinates. Rectangular, or you might know it as, what else do you call it? Cartesian, perhaps. So polar and rectangular. Okay, this is for math. And this is why I ask students to list the calculators that you use, because you need to be an expert at using your own calculator devices to perform mathematical operations, or perform these mathematical operations. Okay, there is a complex numbers practice sheet on the Canvas website. You download that worksheet and you practice performing those calculations on your own calculators. Okay, you need to be an expert at performing these. So polar to rectangular conversion is something that comes from trigonometry. If you extend this, this is a right angle triangle. This is 90 degrees on the right, correct? And then you have theta, the phase angle there. So the quantities are related by trigonometric identities. If you are going from, let's say, if you have rectangular coordinates and you wish to find the polar coordinates, so if you have rectangular coordinates, a plus or minus jb, then tan inverse of b over a gives you the phase angle. And then trigonometric identity. You have a right angle triangle with the two sides as a and b. What is the length of the hypotenuse? Yep. So the length is a square root of a square plus b square. That's the mathematical derivation. So again, these are all tools. This is the information that you've already previously learned. We are going to apply them to circuit analysis. Okay. But as you go along in your education, the smaller steps that you learn, so the smaller fundamental stuff or material that you learn, you will need to apply them faster and quicker than before. Thankfully, we have tools at our disposal. When I was a student 30 years ago, the calculator I had was not programmable. And so we do manual conversion. Now you can use programmable calculators, graphing calculators. You can use online internet tools. You program this equation all at once and it'll spit out an answer in like, half a second. So it's much easier and quicker and more efficient nowadays. But again, These are tools at your disposal. You need to be the expert at using those tools. Okay. If you have polar coordinates, meaning if you have r angle theta, and you wish to find A, let's see, A is adjacent. I'm trying to recall these from memory. I shouldn't have done this. A would be what? Sine theta? No, adjacent would be cosine. Right? Adjacent would be cosine. So this would be r times cosine theta, or magnitude of r, and B would be magnitude of r sine theta. And that's how you would perform the polar to rectangular conversion. But again, these are fundamental equations. You don't have to sit there and do it. This is how we used to do it back in the day. Now you have calculators that can do these calculations directly. Even my calculator from 30 years ago could do a polar to rectangular conversion directly. There are online websites that can do this conversion directly. But in the final exam, you will not have access to the internet. Okay. You will have, well, remains to be seen. Even if you do have access to the internet, you don't want to waste your time going online to a website trying to enter it. It's easier and quicker to do it on your calculators. So every student needs to learn how to do it on your own. You can download the manuals from the manufacturer's website, or you go back to that discussion session, and pretty much most students would use the same calculator devices. So reach out to your peers, reach out to internet sources, and learn how to perform these operations on your devices. One final slide. Again, this is just for informational purposes, is the reciprocals. Sometimes it is more advantageous to work with reciprocals especially when you're working with parallel circuits. And so I just wanted to point out the reciprocal for impedance is admittance. For resistance, it's conductance. For reactance, it's susceptance. Noted YGB, they're all reciprocals. And the units for impedance, resistance, and reactance is ohms. Impedance for admittance, conductance, and susceptance is Siemens. It's named after the German physicist and researcher Siemens, noted by S. Your lab, there is a lab that uses admittance, conductance, and susceptance for parallel circuits. But for theory class, this is just for informational, not for anything else. Okay. So we'll end class here today. If you have any questions, actually, I'll be available later after 3 o'clock. Okay. I will post these lecture videos shortly after I'm done with everything today. And then we'll see you on Wednesday, and we'll go over the examples. All right. Okay, I'm going to take a break, and then I'll be back.